So, last elbow. I'm Krish Patel, a writing senior at the University of Buffalo, and I'll be talking about diffraction-free beams, which is my work this summer with Dr. Phil Strain. So let's get into it. First of all, what was the motivation for this work? Recently, there's been a very hot topic for the past few years, a very interesting prestigious paper for journals such as Optics, the Nature Photonics, Optica Express, on a new claim of diffraction-free beams called space-time wave packets that are diffraction-free. So we wanted to investigate this very interesting claim and really provide some light into its accuracy and physical meaning behind it. So let's get into it. First of all, what is diffraction? I have a nice graphic right here, which kind of illustrates it. But diffraction is a very fundamental phenomenon of all electromagnetic waves. You can think of it as the spreading or diffracting of waves as they pass through openings or slits that cause them to spread transverse, which is that green arrow, relative to its propagation direction, which is that blue arrow. And an important thing we use to look at diffraction is the characteristic asymptotic spreading angle, which is that theta d term, and it's proportional to the wavelength divided by the transverse dimension of the beam. That's that relation right there. So the right side, this is another very simple diagram showing diffraction. The right side of this figure shows a very typical intensity pattern for a diffracting beam. So an intensity pattern is something we look at quite closely when we're looking at diffracting effects of beams. Diffraction is obviously a very ubiquitous phenomenon. It's found everywhere. It's found in lasers, like this right here, microscopes, digital photography, radio telescopes, including especially space telescopes, are actually diffractively limited, so they can only look as far as diffraction allows them to see, and even the human eye. So let's get into, first of all, what we did. First, let's get into the examples of non-diffracting beams. So these are two examples, the Bessel beam and the plane wave, which are mathematical solutions of the wave equation, Maxwell's equations, which theoretically don't diffract. So the plane wave is that image on the top. That's a non-diffracting solution to the wave equation. However, because the planes are spreading, infinitely out into space, it requires infinite energy and is not physically realizable. The other big example is the Bessel beam. So the Bessel beam right there is that bottom image. This is what you would see for a Bessel beam if you just projected it onto the screen over there. And this also has an infinite number of lobes, and each lobe is each circle in that image right there. But this would always also obviously require infinite energy. If you have infinite lobes, you have infinite energy. One thing I want to mention from these two examples before we move on into our investigating the claims themselves is this idea of resisting diffraction. You can theoretically kind of clip the number of lobes in a Bessel beam by making it finite. And you can say resist diffraction because the central lobe, that thing right in the middle, will technically propagate much farther away as long as the outer lobes are absorbing that diffractive effect and kind of giving it energy. So that's true. However, one thing I want to note right here quickly is that it's true that central lobe might go farther, but for your energy to diffract and the propagation distance you're getting, you're not really getting the same bang for buck that you might get for more conventional lasers. So it's kind of more of what you need from the laser. So for this, first of all, before we got into the claims themselves, we looked into developing a very generalized model of diffraction. So Huygens principle is this principle in which case you can look at the behavior of a beam given its initial field. So if I have the field, right here, z equals 0 of the beam, I can know how it works all the way over there into the z direction or the propagation direction. So let's consider a very general pulse to beam equation. This is just the envelope of the beam, and then this is the pulse part of it, and this is the complex conjugate. So this is a very nice general way to look at a beam. And we also considered for this the periaxial approximation, which is just, hey, if I'm shooting a beam in that direction, I'm going to say that it varies very slowly in its intensity as it propagates. And this is quite reasonable when we're looking at diffractively resistant and diffraction-free beams. So for that, we actually managed to formulate an equation. It's kind of a big old equation, but it's an equation that works and it can accurately yield the diffractive effects of a beam as it travels through space. And three terms I want to note right here are this AM term is just the initial amplitude. The J term is the Bessel function. So theoretically, you should use this equation to put an initial amplitude and study the diffraction effects or the propagation effects of the beam as it travels through space. So now let's look into the claims themselves. So these are quotes from those papers I showed earlier on what they're claiming. So they're claiming that space-time wave packets, or STWP, are pulsed optical fields that are originally transported in a linear media without diffraction, And this is done by introducing spatiotemporal correlations into a pulse beam, and that produces diffraction-free light sheets. So let's investigate this. A pulse beam has the following general form, with K naught and omega naught are just the carrier parameters. And the form is just this. All it's saying is that, hey, the field of the beam is just going to be its initial field times this exponent with the negative I K Z, and this K is just the dispersion relation of the beam. And what they're claiming basically is that the condition for non-diffracting space-time wave packets is this thing called space-time coupling, which is achieved when K, this dispersion relation, is basically set to be a constant. So we're saying K is K0. And for this, we actually managed to, and I actually derived this, is we looked into these claims and managed to see, hey, let's say we do this condition for a Gaussian amplitude, what would we get? And we get this equation for the intensity. And this is interesting because if I play this graphic, where this graphic is just the intensity of the beam this is the x direction, and this is z, which is arbitrary because it's diffraction-free in this case. And this 0 right here, and it's going to play the animation, is going to be the time. Let's see what happens. So if I play this, you're going to see the beam is going to uniformly change throughout all of z as time changes. And this is a bit funky. Because a beam doesn't really work like that. So what we found essentially is that when you look into this claim of space-time wave packets, is what you get is this beam that uniformly changes in time, its intensity, which would require infinite energy and very weird Poynting flux as well. And we are claiming that obviously such a beam is obviously physically unrealizable. So this is our investigation so far. So my comments on this work. We have shown that claims of a physically realizable non-diffracting beam are not valid, especially entirely non-diffracting. Our future work, and we've also hopefully presented a generalized form of Huygens principle that can be used to analyze beams and really make sure that propagation and diffraction effects are being properly accounted for. And our future and ongoing work will focus on further claims into space-time wave packets, in which case there's claims that if you kind of relax this condition, you can have basically a resist diffraction, similar to that vessel beam example. So looking into that a bit more, and hopefully we'll have some results on that as well. But yeah, our future work will focus on relaxing space-time coupling, which is claimed to provide physically possible space-time wave packets that are diffraction resistant. So from this, I'd like to show my references and also thank Gavin Blair, PhD student in our lab, for his insight discussions, and also Daniel Serrano, PhD, for his accommodations and help in this program. Thank you.